Hi everyone, my name is Satyaam Raha. Welcome back. So in this video, let us learn about the vanishing gradients problem. So till now we have seen what backpropagation is and how it works behind the scene. Then we have learned two activation functions which are very simple and very common, uh, like the sigmoid function and the tanh function, right? And you know how it works. Now let us understand two problems that are related to these activation functions and which will happen or which will occur behind the scene while you train your deep learning model, and which will not allow your model to converge till infinite time. So it is very important to understand these concepts. So let us start with the vanishing gradient problem. So I hope you remember the weight updation formula, right? Let us go back to that. So in my screen, you can already see the weight updation rule that we have used since the first lecture, right? So if we want to find the new weight, you have to use this formula where you have eta here, the learning rate, if you remember. Along with that, we have something called as the derivative, the partial derivative, right? Now, or this can be said as the gradient of the loss, right? Now just understand this. If we expand this particular thing, so we can write it like this. So old minus it times. Now let us expand this particular term. You already know, if I have to find out, okay, I'll just show you the reference. So for this particular neural network, we have used this neural network, right? So in order to find the derivative of L with respect to W11, so what is W11? So basically you have certain weights over here, right? This is W11. Yes. Now if I have to find this, how do you find out the loss or the derivative of the loss? What is the formula for that? So what we can do is we can, okay, this is the first layer, right? Okay, referring to this particular picture or this particular neural network, let us expand this. How do you expand this? It will be derivative of, first we'll have derivative of L with respect to derivative of O31. Now you see we'll have two paths, right? This is one path up to W11, and from here we have another path. So this one, right? You already know this. So let us just rewrite it. That way it will be very helpful. So derivative of O31 with respect to derivative of O21 multiplied by O21 with respect to O11, O11 with respect to W111, right? This is first term, and the second term will have the second path, which is this second path, right? So O31 with respect to O21, O21 with respect to O11, O11 with respect to W11. That's it. So this is very crucial, you know. That is why I'm writing this like with each derivation. I'm trying to write it, okay, because it is very crucial. You can have so many mistakes is possible here. So let us continue. So it will be O31 with respect to O22 here, right? The second path multiplied by O22 with respect to O11, right? Multiplied by O11 with respect to W111, right? So if we expand it, we'll get this. Okay, we'll use this as a reference to understand the concept. So what we know is these derivatives, all of these derivatives, let us say all of these derivatives, these multiplication terms, it lies between 0 and 1 because of the property of sigmoid or tanh, right? You will always have these derivatives result as either within 0 and 1. So if we multiply anything which is, let's say, 0.2 multiplied by, let's say, 0.5, for a simple example, if we multiply it, what will happen? It will be like this, right? So when we multiply these two terms which are already less than 1 and greater than 0, the result will be much less than these individual terms. That is what we know, right? It is very intuitive. Moreover, let us take another example. If we have like this 0.05 multiplied by 0.03, what will happen? 3 5s are 1 5 15, right? And we will have 4 decimal points like this. So this result is much lesser than these individual multiplication values, right? So if we multiply so many values which are already less than 1, we will get the values which is very negligible, right? The resultant multiplication will be very negligible, right? What is the reason? The reason being the output here, this particular derivation will have a value within 0 to 1 because of the inherent property of sigmoid function and the tanh function. Because the derivative of both of these functions is within 0 and 1, what will happen? We'll always get 0 and 1 here, within 0 and 1. So it will always lie within the result, will always lie within 0 and 1. Same here, right? So obviously when you multiply all these values, we'll get a very negligible value. More the multiplication terms, let us suppose here we have these 3 layers, right? In real life, we'll have n number of layers. Okay, n number of hidden layers. Let us say 1000 layers. Then there will be 1000 multiplications involved. So you can understand all of these values. If we multiply 1000 times, what will happen? You will get a result which is very negligible. Now as a result, you can understand, if we subtract this negligible value from this particular W old value, what we'll get? We'll get a value which is very similar to W111 old, right? We'll get a very similar value because of the reason that these values will be very negligible, right? So what will happen as a result? This W new will be very similar to this particular W11 new will be very similar to W11 old. As a result, convergence will be very slow. We'll have no convergence at all, right? So more the number of layers, the it will take so much time to converge. Okay, so the reason, you understand, because of the inherent nature of the sigmoid function and the tanh function. That is why in the next lectures you will see we'll use some different activation functions in reality because of these reasons. Okay, now the same reason, if these derivative values are greater than 1, what will happen? So we'll see a concept of RNN, the recurrent neural network. In recurrent neural network, we'll use certain activation functions which will give these results as greater than 1. Okay, which will give you certain values. Okay. So in recurrent neural network, we'll be using certain activation functions, not sigmoid, not tanh, some activation functions. I'll not name them now. Let us keep it for the RNNs. Just understand, those derivatives will give you certain values which are greater than 1. Okay. Now what will happen? If we multiply certain values which are greater than 1, let's say 2 multiplied by, let's say, 10, what will happen? We'll get a very high value, very high value than the individual values, existing values. Now if we multiply so many values which are already greater than 1, what we'll get? We'll get a very huge value, right? Now if we subtract this particular result, let us say this result is close to, let's say, 1000. Now if we subtract this from the old W, what will happen? We'll get a certain W which is very different than the old W. We'll get a certain value of new W which is very different than the old W, right? So that is the problem. Now here also the reason is because of the activation function, which has an inherent property that its derivative value lies greater than 1. That is why we'll have the problem where the new weight value will be much different than the old weight value. Now what will happen? Say for example, let me take an example. In case of vanishing gradient problem, what we will see? Let us say the original weight was 0.2. Let us say, for an example, let us say this is W111. Now the next W will be, the next W means the new W will be, let us say, 0.201. Okay, let us say this is timestamp 1, this is a timestamp 2. Okay, let us say in timestamp 3 we'll have W111 is equal to 0.202. So very little change. So what will happen? The convergence will take so much time. Okay, now this is called the vanishing gradient problem. Okay, now what about the exploding gradient problem, which occurs in mostly in the RNNs, where the activation functions will give you certain property where the derivatives of those functions will give you values which are greater than 1. Now what will happen? Let us say originally it was 0.2. In the next timestamp means in the next iteration. In the next iteration, what will happen? This value will be very different. Let us say 0.7. Because we have a value, the reason being we get this particular value as very different. Let us say 0.5. Okay, so 0.2 minus 0.5, what will happen? Okay, so we'll get a value which is very different from the old W. Now because of that, these values will change much. Okay, and the same thing will happen. Let us say in the next iteration we have something, let us say let us take a value like this, let us say 1.2, which is very different, or might be we could see 0.03, right? These values are very different. What is the reason? The reason is simple. We get the derivatives as very large values. This derivative value is very large, and that is why this subtraction will vary very much. Okay, that is why the convergence will be very slow, or it will never converge in reality. Okay, if we show it like this, I'll show it in gradients problem. So let us say my this is my required minima, right? This is the minimum value that I want, and here this is the W, current W. So in case of this particular, see the starting W is, let us say, here. Okay, this is just for visualization. So in case of vanishing gradient problem, what will happen? This is, let's say, W11. In the next iteration we'll have a W11 here. In the next iteration we'll have the W11 here. It will go on like this. So very slow convergence. Okay, because these values do not change much. And in case of exploding gradient problem, this is exploding gradient problem, and this is the vanishing gradient problem. So in exploding gradient problem, what will happen? The original W, let us say here, the next W, let us say here, maybe. Okay, and in the next iteration, maybe here is the next W value. Okay, and this is nothing but the positive axis and the negative axis, like this. So it might toggle like this. From here, let us say the next W will be here, next W will be here. So it will take a very long time to converge to the minima, or it might never converge. That is the issue with exploring gradient problem. That's it for this video. See you in the next lecture. Thank you.